Thank you, Chairman. Good afternoon, everyone. My name is Tomoya Kawabata at the University of Tokyo. Today, I'll be presenting our research on Japan's cryogenic materials development for liquefied hydrogen storage. This research is crucial for the advancement of the hydrogen energy, which is a key component in achieving a sustainable energy future. Here is an overview of the content we will cover today. First one, background and unique point of Japan. Two, history of material for liquefied hydrogen, etc. Firstly, I would like to show you the background. This slide shows energy self-sufficiency ratio in Japan and its history. The upper chart shows that the energy self-sufficiency of Japan is quite low currently, around 13%. The bottom figure is a recent history, which shows it largely dropped in 2011 and then gradually recovered. This is because many nuclear plants were stopped after the Great Earthquake disaster. Even now, it hasn't caught up with the one before the earthquake. Here, the comparison of the renewable energy generation ratio of major countries. Japan aims to catch up with the global leaders in renewable energy adoption, but still much lower, so currently 20%. So Japanese government aims to increase this number to 36%. This strategic shift includes a substantial increase in hydrogen production, storage, transportation, and utilization. Hydrogen policies are being rapidly developed worldwide, as you know. Japan's basic hydrogen strategy has just updated in June 2023. This is the image of industries of the carbon neutrality society issued by the Japanese government. Instead of directly using fossil fuels, carbon capturing technology and hydrogen as an energy carrier and regarded as central technologies in future energy flow. In the middle of this picture, liquefied hydrogen tanks are drawn. The storage system of energy carrier are to be the key to the future society in a resource-poor country like Japan. This presentation is focusing on liquefied hydrogen material, as you know. This is just one method for transportation of hydrogen. Another methods are also being investigating in Japan, MCH, ammonia methanation. Firstly, I'd like to show you the liquefied hydrogen supply chain demonstration. So this content was presented by Takaoka-san, Mr. Takaoka, in last year ISOPE conference. So this was keynote lecture like me this year. So this is different from my research project. Large capacity storage tank issue is not included in this demonstration. This project aimed to establish commercial supply chain for liquefied hydrogen, targeting a hydrogen supply cost of 30 yen per normal cubic meter. So this is corresponding to 0.2 euro, 20 cents. The focus is on developing marine transportation technology and improving liquefaction efficiency. The budget is approximately 1.8 billion euro. This is not a small amount. Similarly, a large-scale demonstration project for the MCH supply chain are underway. The goal is the same as the liquefaction, to achieve a hydrogen supply cost of 30 yen per normal cubic meter by 2030 and further reduce cost of below 20 yen. So this is corresponding to 0.12 euro, 12 cents. by 2050. This slide details one project aimed at establishing facilities to uniformly evaluate the mechanical properties of materials in cryogenic hydrogen atmosphere in Japan. These machines are to be set up in National Institute of Materials Science. This is called NIMS. This project is closely related to my research project. In this slide, the investment for hydrogen gas turbine power generation technology is shown. They are conducting different demonstration operations to verify combustion stability and the other factors, aiming to meet large-scale hydrogen demand by 2030. As I explained, Japan is a resource-poor country, and so I believe Japan own high technology. This kind of country, hydrogen has to be imported from other countries. According to this map in the one website, Korea, some European countries have similar demand. Especially it is said that for Japan and South Korea, hydrogen liquefaction technology is particularly crucial due to their geographic and energy security viewpoint. So so if European country, so pipeline, so this is one candidate, one possible candidate. But South Korea and Japan, pipeline import by pipeline. So this is not realistic. So liquefaction is a very important method if we choose liquefaction. This is very recent news in Japan. The Hydrogen Society Promotion Bill, so left-hand side, and the CCS Business Act were just established on May 24, this year, 2024. So this is very new information. By these laws, it becomes easy for the companies who want to join this field business to invest more. So before establishing this law, hydrogen and CCS should be considered inside of the whole energy governmental policy. So by establishment of these laws, hydrogen and CCS can be independently considered. From this slide, we would like to dive in our project. We have started a material reliability project for liquefied hydrogen storage tanks. This activity is supported by NEDO, New Energy and Industrial Technology Development Organization. This is a subsidiary funding agency from NEDO, from METI Ministry. The period of research is 5 years, from 2022 to 2026, and the reviewing committee. So we established reviewing committee inside of the one academic society, and 29 Japanese representative companies and university are joining this committee. This project started in 2022. Here shows the rated companies and the university in this project. Represented Japanese companies in this field participating. Why do we need to research now hydrogen storage tank material? In fact, not a few liquefied hydrogen storage tanks have been constructed until now. The two left photos are examples of existing tanks. The left one is a tank in Tanegashima, Japan. The middle is the one in Kennedy Space Center. both are for the fuel supply for the space rocket. These are 500 to 3,000 cubic meter class tanks, and both configurations are spherical. In order to reduce the hydrogen supply price, the tank size has to be much larger and larger. This is a supremely important issue at the moment. Tank configuration has to be changed from spherical to flat bottom cylindrical type. Because in the case of spherical, on-site fabrication becomes impossible from some capacity because plate thickness becomes extremely thick, so unrealistic huge fabrication factories become needed. Another reason is the buckling issue in the leg columns, so like here. In fact, the maximum size of LNG tanks is over 23,000 cubic meters. Using flat bottom system, there seems to be much room for larger sizes. On the right-hand side is a rough estimation of the cost of the tank in both spherical type and flat bottom type. Our first target of capacity is set to be 50,000 cubic meters. We believe a flat bottom tank system will be the best solution. The disadvantage of flat bottom type will be BOG. At this point, another technology development will be needed. So what material can be used for large capacity flat bottom tank liquefied storage tanks? This is a big question asked to us, material and fracture mechanics researchers. Regarding materials, stainless steel is mainly used in above ground spherical type storage tanks. Until now, several 300 series stainless steel have been investigated. For example, the VNet project. So this is a Japanese government support type project in 1990s. So in this project, various basic properties at cryogenic temperature and 304 and 316L would be a candidate of liquefied hydrogen storage tank material. And so, however, in the case of airplanes, aluminum alloy had been investigated because lightweight is a more critical problem. Also, in the Space Shuttle project in the United States, aluminum alloy was applied for liquefied hydrogen storage tank. Furthermore, titanium alloy, alpha titanium and alpha beta duplex titanium were used as containers and structure pipes in Apollo space rocket in 1980s. There are other options. Other options may include nickel steel and high manganese steel. Steel manufacturing companies have announced that they have already optimized their categories of steels for use in liquefied hydrogen storage. In our project, we decided two materials are prioritized. Stainless 316L and 13% nickel steel. SAS 316L is favored for its extensive use in spherical LS2 tanks and automotive applications. 13% nickel steel, on the other hand, is preferred for large flat-bottom cylindrical LNG storage tank due to its higher design stress and cost effectiveness. Then, I would like to show you our project progress, material variability research. This slide, very small character. This is an overview of our research program. This slide shows a detailed item list of 2022 activities. This can be divided into three parts. So left side is a design review. And the center part is a material reliability evaluation. And the right-hand side is establishment of guidelines. So we want to establish guidelines for production and maintenance of liquefied hydrogen storage tanks to be constructed until 2030. Now we are doing the second phase, which is a 4-year plan. The activities are divided into 3 categories as well. So several recent project results. So this slide shows the progress point shown. So from now, I'd like to show you the sum of them. So first one is a design side, structural analysis. So design, based on the design parameters, the deformation of the storage tank when subjected to level 2 earthquake motion was clarified using a full 3D shell analysis and 3D solid zoom map analysis. We performed static, so this means simplified, and dynamic, this means realistic analysis. So they have been conducted. In the dynamic analysis, the site-specific earthquake wave, so this is a special word, site-specific earthquake wave of the most severe point, considering the Sagami Trough earthquake. Sagami Trough earthquake is a so that should be specially considered in Japan. Sagami Trough earthquake. So this earthquake wave is being used. Required toughness value will be brought by this structural analysis. Also, we discussed the advantage of applying carbon steel with high yield strength. On the right-hand side graph summarizes the benefit of nickel steel. According to the tentative simplified calculation, the total weight of the side plate is reduced by 30%. So this slide shows that. So by using carbon steel, 13% nickel, the total weight of side plate can be reduced by 30% comparing with stainless 316L. So now the first target is 50,000, but in future the size has to be larger. So in the case of 200,000 cubic meter, the stainless steel, the thickness of the side wall should be too thick. So much higher strength, much higher yield strength steel or material should be used. So in that case, this is one candidate, 13% nickel. So this is the next topic. So this is a J integral critical fracture toughness. So we assume a huge earthquake causes large amount of plastic strain in some tank design through buckling. Toughness degradation due to plastic deformation is a major concern. This slide shows pre-straining in 77K using plate type specimen like this. From the uniformly pre-straining tensile specimen, CT specimens were cut and tested at cryogenic temperature. Of course, pre-straining lead to a lot of martensite transformation, so pre-straining amount can be converted to martensitic transformation volume fraction. Now we got JQ value degradation curve, this graph, degradation curve, not only 77K but also 20K. We carried out 20K experiment using cooling bath filled with liquefied hydrogen. This curve will bring the future judgment whether we can continuously use the storage tank even after a huge earthquake by measuring martensite amount point by point. So if the martensite volume fraction is, for example, 10%, remaining fracture toughness can be predicted by this curve. And fracture study should be done, so based on this degradation curve. Hydrogen embrittlement. This is another topic. Hydrogen embrittlement issue is always big problem in many materials that are applied for hydrogen-related facilities. However, 20K, so this is boiling point of hydrogen in one atom, is too low, even for hydrogen moving into the inside of the ion lattice. So minus 75 degrees C is the most deteriorated temperature. This is our opinion. This is the competition of two factors. One factor is martensite transformation. So this occurs low temperature side. And hydrogen diffusion. Hydrogen diffusion is active at higher temperature. So this competition make this most of deteriorate temperature condition. In this project, we carried out many SSRT tests with pre-straining pretreatment. This is a very new point, novel point. So this is a simulation of the earthquake, and the temperature is a liquefied hydrogen temperature, 20K. If earthquake occurs, the part of the tank is subjected to plastic strain under 20K, so martensite transformation may occur. So results of minus 75 degrees C are shown here. So this graph is base metal and this graph is a weld metal. RRA is a main index, evaluation index. RRA of SSRT test is much decreasing by pre-straining. Left bottom graphic is a schematic summary of this SSRT test. Horizontal axis is the pre-strain amount at 4K. Vertical axis, RRA, is remarkably decreased by pre-strain amount. This is due to microcrack formation started in early deformation stage. Center graphic. This is a comparison of starting point of surface crack formation versus specimen plastic strain. My student carefully observed this crack formation on the specimen surface under various plastic strain conditions. So this is very interesting test result. So this tells us that 10% and more plastic pre-strain specimen appears surface crack in early stage. So 10% or 15%. So on the other hand, virgin steel or 5% pre-strain steel. So in early stage, no crack. And from 40%, the lattice crack, lateral crack, started to occur, initiate. So we think this has to be related with Martensite transformation because, so this is a EBSD image, virgin, so no crystalline state and a 5% state and a 10% and a 15%. So clearly 10% is a starting point of Martensite transformation. So this the starting point of the crack formation, and this degradation is related to, so probably Martensite transformation. Next is the most important, fracture toughness. Fracture toughness is the most critical property in many structural member materials. We checked base plate toughness level first. That is no problem at all, even in 20K and 4K environment. So we are focusing on, we moved to weldment toughness issue, especially weld metal. In tank fabrication, various welding materials, various welding methods are being employed. In this project, real welding methods are applied by a real fabricator of 82 tank in near future. A lot of J1C test at 20K and the Sharpie test at 77K and the 4K weld metal toughness on the vertical axis is not necessarily good like this. We get the knowledge that sufficient performance can be obtained by selecting appropriate welding condition. However, in terms of Sharpie properties on the horizontal axis, the correction among them is not clear. So Sharpie property and J integral critical value, the relationship is unclear. So committee have already investigated the influence factors and their contribution one by one. So for example, martensitic transformation tendency and impurity and delta ferrite fraction. So all of this kind of parameter is incorporated in one equation. We have established the prediction equation from Sharpie 77K to JQ at 20K. One reason of the difference between Sharpie and J1C test appears to be temperature rise in Sharpie test site. You know, Sharpie test is the kind of dynamic test. So this means a high strain rate. And here is a key of the material property, specific heat of this material at cryogenic temperature here is super low. This means plastic dissipation energy is likely to change temperature rise in adiabatic condition. As a result of our dynamic FM analysis, temperature rise of notch tip is calculated to be more than 130 degrees. This temperature rise prevents Martensite transformation in Sharpie test site. So, but the fracture toughness side, the strain rate is very low strain rate test. So the correlation is so this is a one factor for unclear relationship between JQ and Sharpie impact test. We also examine Martensite transformation rate and its relation with stress triaxiality. We developed a special specimen design that is always having a high triaxiality more than 1. So this is a circumferential notched roundabout specimen. And this angle and radius is a key. And as a result of the FM calculation before the experiment, so the center of specimen stress state is like this. Always stress reactivity is always more than 1. So previous study, so for example, this Russian and Ukraine country, 2000 previous paper telling us so stress reactivity, compression, and shear and tension, the tendency is different, but no clear information in higher stress reactivity. But crack tip. So always crack tip stress reactivity is very high. So we need to get the information about that. This is a result, experimental result. Marten's transformation rate measured by ferrite is shown here. High eta. Eta is a stress reactivity factor index. High eta specimen is a remarkably high transformation rate, even at the same plastic strain condition. And the EBSD analysis is also showing the higher martensite transformation in high stress triaxiality. So this is against some previous studies and agree with some previous researches. So this range have remain so unclear. And our study, so as a result of our study, high eta bring high transformation rate of martensite. This is important for judgment of continuous use after a huge earthquake. So we have to do deep discuss continuously the mechanism. Now we are suggesting the appropriate failure scenario considering 316L's various properties. This is quite important for determination of criteria that must be required to the material. Firstly, we assume initial defect perpendicular to annular. Annular means this bottom plate, edge of the bottom plate called annular plate, and this side plate, very bottom of side plate. So this T joint is a very dangerous part. The largest amount of strain occurs in this point. So we assume maximum size of crack at this point. And the assumed size is 1.5 times thickness long and 0.2 times thickness deep based on energy tank assessment. So that is usually conducted in Japan. This defect is assumed to be located at the severest position, like this picture, T-joint between annular plate and side plate. After that, fatigue crack propagation should be considered, like this. The load pattern and the number of cycles should be considered from the actual number of small earthquake and the cycles of depletion and fullness of content, liquefied hydrogen, that the tank receives in its lifetime. So this is a fatigue crack propagation calculation stage. And then we must consider hydrogen embrittlement. As explained before, hydrogen embrittlement never occurs at 20 K. With a full storage tank of liquid hydrogen. In other words, consider the case when the liquid is depleted and the temperature inside the tank rises to high temperature. The fracture deriving force is inner stress, only that is mostly welding resistor stress. Finally, we must assess fracture initiation. So this is a comparison of drying force and fracture toughness. This is a common way. We must assess fracture initiation. This would be evaluated using the R-curve method. As a fracture mechanics parameter, J or CTOD should be used here. Just in the case of fracture occurrence and unstable crack occurred in the tank member, we should guarantee crack arrest property. This is in line with the LBB, leak before break philosophy. In sum, base plates should have sufficient fracture initiation property against this. This will be validated by large-scale tests in this project. From this page, I'd like to show you the large-scale, full-scale test importance and actual establishment of actual full-scale test. In this project, we emphasize on the importance of full-scale test. This concept is based on the catastrophic failure history in low-temperature storage tank, where the first LNG tank was installed in the United States. However, they completely collapsed with a heavy explosion accident that killed over 100 people. Upper photos shows this LNG tank catastrophic accident. The reason of this accident is attributed to the lack of knowledge of fracture behavior of metallic material used, 3.5% nickel steel, too brittle to use LNG tank material for the viewpoint of current knowledge. From this accident, about 20 years was required to realize LNG tank in the United States again. Before this realization, the full-scale test program named Operation Cryogenic was conducted by CPI and the US Steel. These bottom photos are the experiment view. Until now, in Japanese LNG tank construction, full-scale tests have been conducted. Should be required in addition to small-scale fracture mechanics based tests. In this project, we established 3 kinds of full-scale tests that can be conducted at 20K. First one is fatigue test machine with very big cryostat. So inner diameter is approximately 1 meter. This enables real size L-shaped bending test. This will bring direct answer that tells the material this material can be applied or not. So this slide shows several test examples of L-shaped test using cryostat test machine. Applied material, welded joint using standard 316L blade and weld material and fabrication in Japan showed good LCF properties, low cycle fatigue properties regarding to anti-unstable fracture initiation, and low cycle fatigue properties. This test will be the best evidence for actual application. Second full-scale test setup is the ultra-wide tensile test rig. In Japan, there are several test rigs that have 80 meganewton class power Probably only Japan owns this class very large capacity tensor test rig. We have already carried out some wide plate tests with long through thickness crack on weld metal at 20K. Actual JR curve under realistic constant and stress state have been obtained so far. This slide shows the test result of 77K. The original point, noble point, is a cooling bus. So normal, ordinary cooling bus, so by using ordinary bus, so 20K cannot be obtained. So this time, copper, so cooling bus, so made of copper is used. This is a heat conduction point of view. Third one is burst test. Small mock-up tank is fabricated and the surface cracker is machined at the T-joint position. Liquid hydrogen is poured and pressurized by real fuel, hydrogen, liquid hydrogen. By the result of this full-scale test, confirm whether the crack is propagated unstably and arrested or not, whether explosion happens or not. This full-scale test will be the most convincing for whole society and using 316L. This full-scale test site will also contribute on real-size tests regarding concrete dikes. So what is concrete dike? Concrete dike is this. So just in case liquid hydrogen leaks outside of the tank, so this dike prevent the hydrogen going more. Now we are planning 3 kinds of concrete material tests as shown in this slide. So this planning is on the textbook in LNG tank fabrication. This is conclusion. In this presentation, I explained the interim progress of Japanese research project, which covers material reliability in H2 storage tanks. This project will last until 2026. We would like to push for the first realization of the hydrogen society in 2030 in Japan and the world. Thank you very much for listening.